This is the IEEE Computer Society Distinguished Lecturer Webinar Series, brought to you by the Distinguished Visitors Program. The Distinguished Visitors Program delivers tools for individuals at all stages of their professional careers through visits to chapters, offering opportunities for individual interactions, and to the membership through webinars by respected professionals. We have distinguished visitors who cover machine learning, cybersecurity, robotics, big data, cloud computing, blockchain, and cryptography, among others. Chapters can request a distinguished visitor on computer.org/distinguished-visitors. The Computer Society pays all intercity travel, while chapters are responsible for all costs with regard to the hosting of the distinguished visitor, such as lodging, transportation, and food and incidentals in the city of the presentation. The Distinguished Visitors Program is able to pay up to $1,000 for a visit to a chapter, but by working with other nearby chapters to develop a tour, that amount can be increased. So when your chapter is planning its next event, think of the Distinguished Visitors Program.
Hello, everyone, and thank you for joining us today, and welcome to today's webinar, Automatic Image Clustering with Multi-Level Quantum Systems, from our Distinguished Lecturer webinar series. My name is Scott Levine, and I'm the Membership Manager here at the IEEE Computer Society. Before we get started, I'd like to address some housekeeping items. This webinar is being recorded. You'll receive an email tomorrow, which will include a summary of the slides and the recording. You can ask any questions you see on your screen in the Q&A box. If possible, please reference the slide your question refers to. And Dr. Bhattacharya will answer as many questions as he can following the presentation. The field of quantum computing continues to grow at rapid speed, with no evidence of stopping anytime soon. Join the IEEE Computer Society and discover the latest research in the field. Explore the Computer Society Digital Library, home to almost 500,000 peer-reviewed papers and articles covering all things quantum computing. Access IEEE Transactions on Quantum Engineering, the open access journal which features engineering applications of quantum phenomena, including computation, information, communication, and more. Share your insights at conferences such as Quantum Week in 2023, our biggest yearly event on quantum computing, and network with professionals from all over the world. More information will be shared after the webinar, and you can always learn more at computer.org. Circling back to today's presentation, cluster analysis is a popular technique whose aim is to segregate a set of data points into groups called clusters, where the number of clusters are predefined. Automatic determination of the optimum number of clusters form a data set is a challenging proposition in the computer vision community. Different Metaheuristics are widely used for solving complex organization problems. In this lecture, the use of multi-level quantum logic and metaheuristic techniques is explored to design quantum metaheuristics, which can be applied to compute optimum number of clusters in a data set to obviate human intervention. Dr. Siddhartha Bhattacharya completed his bachelor's in physics, bachelor's in optics and optoelectronics, and master's in optics and optoelectronics from the University of Calcutta in 1995, 1998, and 2000, respectively. He earned a PhD in computer science and computer engineering from Jadavpur University in 2008. He is the recipient of several coveted awards, including the Distinguished HOD Award and the Distinguished Professor Award conferred by the Computer Society of India Mumbai chapter in 2017. Is the Honorary Doctorate Award from the University of South America and the East Asian Regional Computing Confederation, and the International Digital Award ICT Educator of the Year in 2017 as well. He is currently the principal of Ranchigar Mahavidyalaya, Birmingham, India. Before this, he served as professor in the Department of Computer Science and Engineering at Christ University in Bangalore. He served as the principal of the RCC Institute of Information Technology in Calcutta from 2017 to 2019. He has also served as a senior research scientist in the Faculty of Electric Engineering and Computer Science of BSB Technical University in Ostrov, Czech Republic. Prior to this, he was a professor of information technology of the RCC Institute. He is also the editor of the International Journal of Pattern Recognition Research and the founding editor-in-chief of International Journal of Hybrid Intelligence, Indus Science, and is an associate editor of a few other journals as well. Dr. Bakatara, thank you for being here with us today, and the floor is yours.
Thank you, Scott, and welcome all the participants for this webinar. So today we'll be just discussing about this very valid and relevant topic in the present scenario, the problem of image clustering or the clustering of data sets actually require the human intervention or supervision from outside in the fact that you need to input or rather need to provide the number of clusters, target clusters or classes in which a particular data set needs to be clustered. And oftentimes in real life situations, you do not have this information regarding the number of clusters, and you have to determine it in real time. So it becomes a quite difficult task given that all the existing algorithms are relying on this number of clusters which has to be provided beforehand. Or rather, you have to have a priori knowledge of the number of clusters. But then the challenge is how to make it automatic. That means you do not require any human intervention as such. The algorithm itself will determine the number of clusters on the run, on the fly, and will just cluster the result for you. And added to that, the entire topic is also being conjoined with a new recently or rather coming up, rather recent computing paradigm in the form of quantum computing. And now that means that this particular topic is actually interdisciplinary in nature, where you have these clustering algorithms and then combined with these quantum systems. And now the pertinent question comes into our mind that why quantum systems at all? So now you see that there's a buzzword all around. Quantum computing is now being researched widely all across the world, thanks to the different players in the industry who are just coming up with different systems. Each and every day, if you look at the different feeds, news feeds will get updated information regarding the evolution of the quantum computers. And now this particular system is expected to perform more efficiently compared to the classical and conventional computers. Even putting together all the supercomputers of the world, they can excel them in all possible ways. So that is the hunch behind this particular topic, where we try to just put together the ideas which are relevant to the quantum computing paradigm and which make them efficient with regards to the classical computing paradigm, and then try to just design some algorithms which will help us to automate the image clustering process. So let us move on, and it will be clear if you just move to the next slide where the layout is given. We'll be first discussing about the clustering essentials. What is clustering? What does clustering mean? And what is the good clustering? How can you tell that whether a clustering result is good or not? And then moving on to some other aspects of clustering in the form of hard clustering versus soft clustering, that is fuzzy clustering or piece clustering as such. Then whether a clustering process is giving you the best possible results, you have to have some quantitative measure. And then in that case, the cluster validity indices or metrics come into play. They help you to give an insight into your clustering outcome and whether the clustering outcome is a good one or not. And then touching upon the quantum computing fundamentals, because within the scope of this lecture, it is quite difficult to cover up the entire thing. But then just to give an insight into the quantum computing fundamentals, we'll be having some idea about the brief idea regarding the very basics of the quantum computing, which are required for development or evolution of the algorithms in mind. And then automatic clustering, the central problem of this particular topic. Why at all we are going for automatic clustering? and what are the possible ways to make it automated in nature. And then we'll be just delving around these classical optimization algorithms, conventional optimization algorithms, very well-known algorithms. We'll be touching upon 3 of them. And then finally, we'll be just giving some ideas regarding how these algorithms, these classical optimization algorithms, may be designed using the quantum computing algorithms. That means make them quantum inspired, not purely quantum, but maybe some quantum classical or hybrid quantum algorithms in form to automate the clustering process. So this is the outline of the lecture. We'll be starting together with the definition of clustering, very basic thing. And it is actually a way of grouping data samples. So when you have some data set in your hand and you do not know the distribution of data and all this and the features and all these things, so you have to have some mechanism to sort out the data or to group the data into several clusters or several classes, depending on some features, depending on some other aspects, other characteristics of the data. And the main concern or main consideration while clustering a particular data set is that you have to ensure that the documents or the objects or the points or the data points within a cluster should be similar to each other, should be as similar as possible. And also, documents from different clusters should be dissimilar. That means we have to segregate the different clusters in a quite better fashion so that the data points in one cluster do not overlap with data points of another cluster. Now, obviously, there are some other variations of this particular concept, but then the basic idea is that you have to have the clusters in that particular form where the points within a particular cluster should be similar to each other with respect to features, with respect to other characteristics, and also ensuring at the same time that the documents from different clusters should be dissimilar. And as such, it is already a form of unsupervised learning, but then there are some different conjectures because already we have discussed in the first, in the introduction, that means these clustering algorithms require some human supervision in the form of inputting the number of target classes and all these things. So actually speaking, one particular school of thought, they generally prefer to take these clustering algorithms as supervised in nature. However, they are in general, they are meant to be unsupervised in nature, but with the exception that if you just set aside the number of target clusters, then it becomes unsupervised in nature. And obviously, it is a form of data exploration where you explore the entire data set and try to just gauge on the features and characteristics and try to just group the data set to the data points together based on their features. So now you see one example is there. You see some data points already scattered around the space, and here you can just, quite obvious, you see that this, you cannot just, for example, in this particular example, you can see that there are 3 clusters marked by 3 different colors, yellow, blue, and red. But the interesting thing is that you see these particular points, for example, I don't know whether this mouse pointer is visible to you or not. This particular cluster, the yellow point, it is quite difficult to judge whether this particular point is going to be a part of this yellow cluster or blue cluster or red cluster. So that is the uncertainty behind this entire process, because most of the clustering algorithms do not generally give a very definite outcome. It depends on the particular algorithm and the number of features and the number of clusters. All these things decide the performance of any algorithm. But in any way, we are in a position now to determine, to say that the entire data set can be divided into 3 different types of clusters by running any particular clustering algorithm. And now you see one example is given, a small animation regarding the k-means clustering. What you see initially, you start with the data points, you pick some random points like this over here, these arrows are random points or referred to as the cluster centroids. And then by means of some iterative procedure, try to just group the data points together in one particular position, and with respect to these individual random points initially selected. So then you just come up with these 1, 2, 3, 4 clusters. So this is actually iterative process until and unless you arrive at the best possible outcome. But then again, it is not actually uniform in nature. Different algorithms will give you different outcomes. Now, so you see the same example has been repeated with the total within cluster sum of squares metric. That means you try to minimize this entire metric. Another example of a k-means iteration, 1 by 1 iteration, But you see that the data points are there, and this process are the initially chosen cluster centers, which generally gets updated with time until and unless you reach convergence, or the algorithm converges, where you get the clustered output as such. So you ultimately see it is ultimately when they converge, you get 4 different clusters like this. So this is the procedure, but then the main problem over all these algorithms is that you see you have to give the number of clusters before that. That means you have to provide the algorithm with the knowledge regarding the number of clusters, whether it is the number of clusters is 4 or 5 or 2 or 3, it depends. So depending on your choice, depending on your input, or depending on your supervision, the algorithm is going to perform. So there is no way as such that the algorithm can itself determine the number of clusters and on the run, and can cluster the data set. So that is the main challenge which we are going to address in this particular topic. So now comes the question, what is actually good clustering? How do you ensure that it is going to be a good result or good outcome of your algorithm? So quite obvious, if you have a data set, we are comprising n number of points, x1 to xn, and then you try to just cluster this entire data set into p number of clusters. So again, you know the p before that, isn't it? So the number of clusters is p, and so you have different clusters c1, c2 to cp. So you are dividing or segregating the entire data points into p number of clusters. So if you have a good clustering algorithm, you should ensure that no cluster should be null. That means should be a null set. That means at least one single point should be there in one particular cluster. No cluster should be there without any particular data set or data point rather. And also there will be no overlap between 2 different clusters. So the intersection will be a null set. Okay. And also the union of all the clusters will give you the universe of discourse or the entire data set as such. So actually speaking, these are actually crisp clustering, where you do not have this option of overlapping between 2 different clusters. So that is quite obvious, because these particular algorithms are based on this yes or no, that means true or false clause. That means whether a particular point is going to belong to a particular cluster or not. That is the main concern of these algorithms. And then, given this background, what is the objective, or what is the essential consideration behind the good clustering process? First of all, you can have the internal criteria, where already we have seen that you have to ensure that the intra-cluster similarity is high. That means the similarity between the different data points in a particular cluster should be very high. That means highly similar points should be clustered together. In contrast to another point, that is interclass similarity is low. That means the similarity between the 2 different clusters should be low. Within a particular cluster, you have the highest similarity possible, and within different clusters, you have the lowest similarity possible, the highest dissimilarity. And so that actually governs any particular clustering algorithm, and every clustering algorithm tries to maximize this first point, that is, maximize the intra-cluster similarity and minimize the inter-cluster similarity. And then you have already discussed that all these are crisp clustering in nature, where you have only one single opinion that each document belongs to exactly one cluster. And that is not, you do not allow a particular document or a particular object to belong to 2 different clusters simultaneously. So you have either a true or a false situation, where you have a particular point in the feature space to belong to a particular cluster only. But then a slightly different variant is the subclustering or fuzzy clustering, where you have this flexibility, where a particular document can belong to more than one cluster. It becomes quite obvious, because you see, for example, if you take a pair of sneakers, okay, the pair of sneakers can either be clustered in a cluster of sports apparel or shoes. In both the cases, it is true, because the sneakers can be classified or clustered, or can be designated as a sports apparel. At the same time, it can also be treated as shoes. So you see, it just actually belongs to both the clusters, that is the sports apparel and the shoes as well. But if you just go for the hard clustering, this particular concept is not clear. Only either you put the sneakers in either of these, that is either the sports apparel or the shoes. So if you put that in a sports apparel, obviously it is not going to belong to shoes at all. You cannot treat the sneakers as shoes. But this actually, that means it is quite flexible, more flexible approach, where you have this option of overlapping between two different clusters, or a particular or a number of points, a number of objects can belong to both the clusters, which obviously with some degrees of belongingness. So it is not that they are belonging to both the clusters with the same degree or the same characteristics, but it is that it is going to belong to different clusters in different degrees. That means maybe in some particular cluster it is having a higher containment, in other cluster it is a lower containment. But at the same time, it is a true fact that it is going to belong to both the clusters simultaneously. So now these are some of the examples, not an exhaustive list, where you have this application of clustering in several areas of science, technology, business, medicine, everywhere. You find this example, and it is now widely researched and widely used all over the disciplines, including biology, information retrieval, land use, for example, demography, then climate understanding. For example, you can also use the clustering for clustering of the hyperspectral images taken from the satellites and all these things. So just to have an understanding of the variation of the information over time. So the temporal information can also be retrieved using this clustering example, because, for example, if you were just going to cluster in a hyperspectral image or a satellite image at one point of time, say at one point of the time of the year, and then you do the same clustering after, say, another 6 months or so, and then you can just, from the results, you can just gauge, you can assess whether there is a change of vegetation or change of the demography, all these things. So this clustering tool is quite useful nowadays and are being widely used all across the disciplines. Now, given all these things, so the different forms of clustering can take place, different forms of algorithms are there in place. So based on different criteria, for example, the partitioning criteria, while you have the single level clustering or hierarchical partitioning, depending, that means you partition the entire data set either on a single run, or just we have shown in the case of a k-means or some other algorithms, but maybe also you can go for some hierarchical partitioning from the top-down approach, just to go for, that means breaking or merging regions like that and arriving at the final outcome. Or else you can just think on the, concentrate on the separation of clusters, maybe which is exclusive, as in the case of a hard clustering, that one customer belongs to only one region, versus non-exclusive, where you have one document may belong to more than one class. We have already discussed it earlier. And also maybe based on the similarity measure, that means the similarity, the intra-class similarity which you are going to maximize, whether how the similarity is going to be computed or evaluated. Either it will be distance-based Euclidean metrics you can use, any sort of metric you can use, or connectivity-based. And again, you can also embark on the clustering space. You can take the entire clustering space or feature space as a single space to work upon, or you can also divide it into different subspaces and then go for clustering on the different subspaces individually, and then finally merge the result together. So it depends on the complexity of the problem and the type of data, and also the size of the data under consideration. And based on these, you have different clustering approaches, like the partitioning approach, which generally the very important one is the k-means, k-medoid clearance, where you construct various partitions and evaluate them. Or hierarchical approach, where you go for a hierarchical decomposition. Like these are some of the examples, the Camelon and all these things are quite widely used and very renowned algorithms, or density-based approach or grid-based approaches. So different types of approaches are there, and also you can also come up with your own algorithm as such, which may be either of these or may fall into either of these categories, or maybe a new one altogether. Now, the point is that we have given some background of the clustering process, what is the objective of clustering and how it is actually done, maybe some a brief idea. But then how to determine whether a particular clustering outcome is good or not, whether there is any metric or not. That means you can determine, you can evaluate the metric, and then find out some quantitative measure as to how good is the cluster your algorithm is giving up. So you see, then the pertinent question is, why do you want to evaluate them? First of all, is that whether the clustering is good or not. That is one thing. Second is that you can, if you have any particular metric at your disposal, you can compare two different clustering algorithms. Which one is better than other? You can also compare two set of clusters, or you can also compare two clusters. So you see, the clustering algorithm is not at all subjective in nature. These are objective, because you can just measure the performance of any clustering algorithm using some cluster validity metrics. or indices as they're called. So, so you see, for example, it will be quite obvious. If you see the example, you see some random data is spread over there, random points are there which are not clustered. Okay, all are marked in red. If you run this DB-scan algorithm, clustering algorithm, it will just give up you 3 clusters like this green one, this bold blue ones, and this blue one. And now if you run the k-means algorithm on this data, you will get these 3 clusters, but the orientation of the 3 clusters will be different. You see here, all these points belong to the same cluster in the case of DB-scan, but here k-means has segregated that into 2 clusters like this, and the remaining points have been put in a separate cluster. So with the number of clusters being set to 3 in all the cases, the DB-scan, k-means, and the complete link, they are giving different results. So how to judge whether which particular algorithm is giving you the best possible outcome? Then you have to resort to this clustered matrix, validity matrix. That is why that is quite important in this particular context. So then, what you want to do actually, you have to just validate the clusters. You have to try to just distinguish between whether there is any non-random structures are there in the data or not. You can compare different cluster results to see whether the particular clustering outcome is quite relevant for your problem. And then also you can just go for using the data to fit, using your outcome to fit the data. Already you have some, maybe since already I have told you that some school of thought, they treat this clustering algorithm as supervised form of learning. So you can also have some label data where you can just have your algorithm run on the data and then just compare it with the label data, whether your outcome is matching with the labels. And also you can also determine the correct number of clusters, because these clustering and validity indices will give you some result or some indication whether the correct number of clusters has been found in the outcome or not. So now you see, just focus on this particular point, point number 5, determining the correct number of clusters. So that is the objective behind this particular topic. So if you can design some algorithm which can find out the correct number of clusters from the data itself without having, or rather without requiring to keep or provide any number of classes beforehand, then your entire process becomes automated. So objective is to just try to devise an algorithm to find the correct number of clusters in any particular data set without having knowledge about the number of clusters beforehand, without having knowledge about the levels of the data. So in that case, what actually happens, so you just feed the data to the algorithm, and the algorithm automatically finds out the correct number of clusters and then cluster the data. So that makes the entire process automated in nature, and that will be the focus of this particular topic. So you see the different measures of cluster validity indices are there. These are some of the examples, and all of these particular measures actually they are based on this either an external index where you measure the entropy of the data after clustering, because a random data will always exhibit high entropy. So once you cluster them, they will get some entropy values which you can just measure to find out the validity of the clusters. Also, you can go for the sum of squared error or any other combination of the SSE or entropy as such. So depending on this particular type of indices, there are different types of cluster validity indices. Some of them have been listed here. For example, the Dunn index, very famous one. In 1974, it was just proposed by Dunn, or mainly for k-means clustering, actually. So you see the objective of this particular index is to identify compact and well-separated clusters. Compact means, that means the intra-cluster similarity will be high, and the inter-cluster similarity will be low, well-separated. So this is a formulation where you see xi, xj are 2 different clusters, and delta is the distance between the 2 different clusters. Maybe you can use either Euclidean distance or Minkowski or any other metric you can use. And this is the inter-cluster distance. This is the inter-cluster distance and inter-cluster. So you see, the objective is that given this, where delta xi, xj is the inter-cluster distance, and this is the intra-cluster distance. So the large values of V will be giving you good clusters. Why? This is the inter-cluster distance. If you just go on increasing the distance between the different clusters, that means if you are ensuring that you are trying to maximize the dissimilarity between different clusters, that means the distance between the clusters will increase. So the numerator will go on increasing. At the same time, we are trying to minimize this one, that is the intra-cluster distance, that is distance between the points in the same cluster. So the numerator goes on increasing, denominator goes on decreasing, so ultimately the entire factor comes out to be maximized. So it becomes higher. The higher the value, the better is the clustering. So higher is the value of V, you will get the better clustering. So you try to just devise a clustering algorithm and apply this. Once you get an outcome, you get all the data points segregated into different clusters. You try to evaluate this particular distance metric or this Dunn index. And the value of Dunn index will give an insight whether the clustering has been good or not. If it is very high, the value is very high, it is going to be good. If it is low, it is still requires improvement. Another similar index is the Davis-Baldwin index. In this case, it is actually the reverse one. You have to minimize this DV index. That means given this formulation, you see that it's the reverse actually, where you have the intercluster distance in the denominator. So you have to ensure that the centers are very far away from each other and the clusters are compact. But then the formulation ensures that you have to minimize DV to get the optimal number of clusters, the good number or the best number of clusters. And another one is the similarity coefficient, where again, same thing is similar types of thing where you calculate some two values like A and B is the average distance of the of a particular data point I in a particular cluster to the points in the cluster. That means the same cluster, the distance between I and all other points in the same cluster is A, and B is the minimum of average distance of that particular ith point to the points in another cluster. So this A is measuring actually distance between the point I or the data point I to the other points in the same cluster in which I is belonging, and B is that between other points of different cluster. And then you come up with this particular formulation, and the closer the value is going to be equal to 1, the better. So the value ranges from 0 to 1. The higher the value means, it is the better. Finally, you have this I index, another type of index again. You have this entire thing where you have this maximizing criteria. You have to maximize this I index, where again you have the intercluster distance between the points in the same cluster given by the expression EJ, and DJ is the intercluster distance. It is the distance between two different clusters. So obviously you have to try maximize that, similar to the Davis Dunn index, where you have to maximize the I index. So several different authors or researchers have come up with different indices, and also other indices also coming up, having their own advantages. And obviously the complexity of the algorithm also makes sense. So different indices can be used for measuring whether, judging whether your clustering outcome is a good one or not. Now, given this background on the clustering algorithm, we'll be just touching up on the basics of quantum computing. So you see, quantum computers is not the only one. It is maybe one of the ways, one of the alternative ways of conventional computing, because there is a conjecture that Moore's law is going to fail after 2030s. Then what after that, and whether there will be an expansion or just improvement in the performance of the classical computers, because you cannot just go on increasing the number of components in an integral circuit after a certain limit. So that ultimately means that Moore's law is going to fail. So what after that? So maybe quantum computing may be one of the alternatives which is going to address that particular situation where you have reach the limit of performance in terms of the speed, number of threads, number of coprocessors in a classical computer. So based on this, the quantum computing is one of them, and it is based on the principles of quantum physics or quantum mechanics. And any particular quantum system actually, it actually emanates from the Schrodinger's principle of uncertainty or wave particle duality, where you can just visualize any particle as a wave and vice versa. So any particular wave or any particular particle or quantum system can be characterized by a wave function in this form. This particular notation is referred to as a Kate notation, KET Kate notation. I'm afraid I do not have any pointer as such over here or any other tools to point it out or to write something over here anyway. So the Kate psi or the wave function is given by this particular expression, which is actually a summed up expression of a CJ, a complex coefficient CJ, and another wave function phi j. So these 5J, or these are referred to as the computational basis or the qubits. And the interesting thing is that the basic unit of quantum computing are the qubits, which are the fundamental elements, which are analogous to the bits in classical computer. But then with the difference that bits in classical computing, the bits can manifest themselves either with a value of 1 or 0, but not both values. It cannot hold both values together. That means you can either have a value of 1 or a 0 to a particular bit in a classical computer. But the difference with the quantum computer is that the qubits, they can actually exhibit multiple values at the same time. That means they can have a combination or superposition of different values of 0 and 1. So what is the advantage you are getting? Advantage is that you can start a solution. You can have a variable or any particular solution of any particular problem being encoded in the form of qubits, which are actually superposition of several different possible solutions. And then you start up the algorithm, and then the only challenge remains to find out the best solution out of all the possible solutions which are present in a qubit. So that is the advantage. That means you are just equipped with all the possible solutions which are actually existent. But in the classical case, what you do, you start with a particular solution, you try the algorithm, you just run the algorithm, you get the outcome. If the outcome is good, then it is okay. Otherwise, if it is bad, it is not up to the mark. You again run the algorithm again with a different solution altogether. That means there is no option to just run the algorithm with a multiple number of solutions, all possible solutions at the same time. So I'm just giving some brief overview, some examples, but the detailed treatment is beyond the scope of this lecture. So the basis of the quantum states are designated as this Gate 0 and Gate 1. So these can be represented, these are the electron spins, either a spin up or a spin down. So either a ground state or an excited state, the electron spins can be represented by this Gate 0 and Gate 1. If you are embarking on a superconducting technology, but if you are going for a photonic quantum computer, which is another form of quantum computer, you have this polarization of light, either vertical polarization or horizontal polarization. So things vary, but then these qubits, Gate 0 or Gate 1 are represented as a column vectors like this. Gate 0 is represented by 1, 0, and Gate 1 is represented by 0, 1. So these are the two individual qubits of computational basis states, but then the interesting thing of the important thing is that any particular qubit or wave function is actually a combination or superposition of several different qubits as such. Okay, so you have a combination of Gate 0 and Gate 1 together. So in a 2-qubit system, you have a wave function can be represented as a combination of Gate 0 and Gate 1. For example, alpha Gate 0 plus beta Gate 1, where alpha and beta are complex coefficients. But ensuring that alpha square plus beta square should be equal to 1. Because these are actually probability amplitudes, alpha and beta, and the sum of the probability of any particular event is always going to be 1. So we have to ensure that alpha square plus beta square is equal to 1, which actually means what is referred to as a quantum orthogonality. So we'll be using that quantum orthogonality in our problem. So finally, we end up that any quantum computing system is characterized by these 2 qubits, basic computational basis states, which can exist in superposition. So that you can have multiple or multitude of solutions at the same time at your disposal, and then you can just design an algorithm to manipulate the qubits in such a fashion so you arrive at the outcome in no time or other, in very lesser time compared to the classical algorithm. So you see also, similar to the classical machine, you have the different gates, logic gates over here. These are standard gates to operate on the qubits to give us some outcomes. For example, the Hadamard gate. The Hadamard gate actually is responsible or main for creating the equal superposition of 2 qubits. So initially speaking, if the electron spin is either aligned to the up or down. So if you apply Hadamard gate, you will get a equal superposition of these electron spins up and down together. Or you have the rotation gate where you can manipulate a particular qubit to either align nearer to the Gate 0 axis or the Gate 1 axis. Again, the NOT gate is there where you have the inversion or flip of a qubit. Flip of a qubit means you can change the probability amplitude only. Not that you cannot change the electron spin, but what you can do, you can just change the probability amplitudes. So anyway, so you see one example is there, a qubit alpha beta. Alpha is the probability amplitude for Gate 0 and beta is for Gate 1, can be updated by using this particular matrix. So actually speaking, all the operators, all these logic gates are there. These are actually unitary operators. So actually unitary operators or unitary matrices. So what actually boils down, you are actually multiplying a matrix with a vector. So you automatically get a vector, new vector. So new vector means the updated one. Where updated one means, so this cos theta and sin theta, that means theta angle is the angle of rotation you are applying on this qubit. So qubit is a wave function, so obviously it has some phase. So sorry. The objective is to change the phase of this qubit or the wave function by angle theta. So either you have for example, if the initial phase of the wave function of the qubit is phi, so after application of this rotation, you will get a new wave function with a phase of theta plus phi. So already we know that from our childhood days that multiplication is the shortest form of addition. So ultimately what you are doing, you are adding the two phases together by means of multiplication. So these operations are there. So the very standard operations can be used to manipulate qubits. So what is the outcome you are getting? Your outcome is that you are getting a new qubit, new orientation, with a new orientation. Either with the effect of this angle theta, it is going to be aligned nearer to the K0 axis or the K1 axis. So the high probability now, if it is going to be manipulated in such a manner, rotated in such a manner that it goes nearer to the K0 axis. So at this point, if you go for measurement of this system or try to observe the system, you will get an outcome which is likely to be 0. So actually speaking, what is the objective? First of all, you just get a problem or take a problem and just convert that problem into quantum domain by means of encoding the solutions or the trial solutions in the form of qubits. Then you manipulate the qubits, run your algorithm, quantum algorithm on the qubits, and then finally you arrive at some quantum outputs in the quantum domain. And obviously speaking, if the outputs are in the quantum domain, no user or any human being will not be able to understand, because human beings are more accustomed to appreciate classical values. So you have to again revert back to the classical domain. This reversion back to the classical domain is referred to as the measurement. It is measurement operator you apply on the qubits, then you get either a 0 outcome or a 1 outcome. So ultimately you end up with 0 or 1 depending on the probability values of alpha and beta. But then I told you that this is beyond the scope of this lecture. Just for the sake of understanding, I'm just giving this brief overview. And then this is the very intrinsic features of quantum computing. Linear superposition already have discussed that any particular solution can be, or a combination of particular number of solutions or number of qubits can also be a probable solution to your problem. And interference is also a familiar wave phenomena where two waves or two waves interfere constructively when they're in phase and interfere destructively when they're out of phase. And entanglement. Entanglement is another interesting feature, and it is being widely used nowadays. So what actually happens over here, when you take two qubits and try and make them interact with each other. So what actually happens in the layman's words, the qubits try to inherit each other's properties. So the properties of one qubit gets inherited by another, and the properties of another qubit gets inherited by another. Just for the layman's word, I'm telling you. So just what actually happens, so they become entangled, and they are referred to as entangled pair. So once they become entangled, as if they are actually copies of each other, they're replicas of each other, because they have already inherited the properties of each other. So now at this point, if you take one of the isolate the pair, that means you take one of the qubits from the pair and just move it to a very remote distance with no physical communication between them. And then if you try to measure, rather go for conversion or the reversion of that one particular pair or one particular part of the pair using measurement operator at one place, the same effect will be automatically reflected on the other pair as well, or other part of the pair as well. That means since they are copies, so sometimes actually these are referred to as Einstein's spooky action at a distance, as if when you are just going for giving an operation on any part, on one part of the entangled pair at one point, the same effect is automatically getting affected on the other part. That means you do not have to apply measurement separately on the two pairs, on the two parts of the same pair, different separately, but then measurement at one end will automatically affect the measurement at the other. So if one particular part of the pair is giving you an outcome of 0, the other one is going to give you an outcome of 1. So that is the very interesting thing. That means as if the information is being transmitted or percolated between the two qubits, whereas in the actual scenario, you do not require any physical communication as such, because initially when you entangle or interact, the two qubits interact each other, they become entangled and as if they become replicas of each other. So any effect, any operation on one part will automatically affect the other part as well. So now, given very brief idea of this quantum computing paradigm, we'll be just touching upon or see whether why this particular problem, automatic clustering, is at all needed and how you can solve it. How you can just go for trying to devise an algorithm which can automate the entire process. Okay. So you see, already we have just discussed this earlier, that it is supervised in nature because you require the human intervention of the number of clusters. And given this particular problem, you require human intervention. So that means you require the target number of classes, the information regarding the target number of classes. You have to know beforehand the target number of classes in which your algorithm is going to cluster the entire data set. Okay. So that is the main concern, our main limitation or main hindrance behind making this entire process automated in nature. So one of the possible solutions is maybe to determine the optimal number of classes. So if you can just devise an algorithm, obviously optimal means obviously you have to apply some optimization algorithm. You have to optimize the entire clustering process. So you can use the optimization algorithms to achieve the automated clustering, because the optimization algorithms can use the cluster validity indices or metrics to determine the optimal number of clusters, and then you can just find out some ways of determining the number of clusters on the run without having intervening, without requiring any human intervention. Because in that situation, you do not require to give any target number of classes. You just run the algorithm on the data set, and the data set and the optimization algorithm optimizes the data set, but optimization the entire clustering process using different objective functions in the form of these cluster validity indices or metrics. Maybe either you are using a turn index, TV index, I index, or silhouette index, depending on your situation. And then you arrive at the optimal number of clusters. And then again, you go for measuring the cluster validity and see whether this optimal number of clusters which is coming up is good enough to adjudge your algorithm to be the best one. So actually this entire objective is twofold in nature. First of all, you can determine the number of clusters automatically. And second one is also at the same time you can determine whether your clustering algorithm performance is good or not, whether you are getting good clustering or not. So this is the objective, and this is the entire focus on which the algorithms can be used, or these clustering algorithms can be changed or can be modified to just come up with some automatic clustering processes where you can determine the number of clusters on the run without requiring any human intervention as such. So before moving into that, you have to just browse up in some different classical optimization algorithms, because all of these are very well known to you anyway. For the sake of completeness, if you know the genetic algorithm, it was devised by John Holland in 1970s. So it is based on Darwinian paradigm, where you have this reproduction, then competition, selection, and survive. So it is actually iterative procedure. You start with a trial solution, a population. These are population-based algorithms. You try with a trial solution, and then you run the algorithm, see whether the trial solution is better enough to move forward, or you reject that. And then again, you go for some operations on these, like operators like reproduction, crossover, mutation, etc., to come up with a new set of trial solutions which are better than the previous one. And at the same time, rather holding on to the best possible solution at any particular point of time. So now, after convergence, you come up with the best possible solution of the particular problem, best possible optimal solution to a particular problem. And then this is the conceptual form of the algorithm. You initialize the population with some random solutions, trial solutions, and evaluate the fitness of the solution, whether the solutions you have, because these are generated randomly. So the interesting thing is that you do not require any context information regarding the problem. You do not require any problem regarding the data set or any other. For example, if you are going to cluster a data set with this algorithm, using this genetic algorithm, you do not require any information regarding the data set. But then that means you start with a random solution, random set of solutions, evaluate the fitness of the solution based on some metric, And then you go see whether these algorithm has converged or not, first of all, or else whether the solutions are good enough or not to continue. If they are good, then okay, you just output the results. Otherwise, you again select some survivor by means of reproduction mechanism, and then you randomly vary the individuals, applying the operators like mutation, transfer, etc. And then you start all over again. You again evaluate the fitness, again you start all over again. So this is actually iterative procedure. After finally, at the end, you end up with some outcomes which are very relevant and which will give you some idea regarding the optimal solution of that particular algorithm for that particular problem. So it is actually, you see, it is actually inspired by natural evolution, survival of the fittest, and then you start with again population of individuals. Then you just evaluate the fitness function based on some fitness objective function or fitness function, and then you go for creating new generations depending on the fitness function. Just sort the fitness values, choose some better solutions, and then try to just go for some operations on them to give rise to different offsprings with the conjecture that the offsprings are going to give you better outcomes. So that is a process which is inspired by natural evolution. And then, so the offsprings are having combination of properties of the two parents. So it may happen that the parent, a part of the parent is having good values and rather having probability of giving good outcomes, and another parent may not have a probability of good outcome. But then if you go for the mating of these two parents, then it may happen that the new outcome or the offspring may have some good probability of having qualifying as the best solution. And then you just go for a new generation. You can depending on the strategy you're using, you can either discard the worst solutions and only keep the new better solutions, and then you go on again until it converges. So basically speaking, all the algorithms actually speaking are generally based on this particular procedure. Maybe there's some variations in respect to the number of different operations or the encoding mechanism, etc. So you see another algorithm is that vertical sum optimization, PSO, very widely known and very efficient one because the number of parameters is very low compared to other algorithms. So it was developed by Everett and Kennedy, and it is actually inspired by the behavior of swarms or insects. And then what you do, you try to just start with a trial, some set of trial solutions comprising what are referred to as particles, and then you compute their current position, velocity, etc. And then on each and every iteration, you update the velocity and position, and try to just gauge which one is coming out of to be the local best and the global best. That means you try to just, there is a competitive procedure where each and every particle try to compete with each other, not only with each other, but also with the best possible one of all the particles. So each and everyone is competing among themselves to be the best one or to excel in terms of the performance. So another form of algorithm, but maybe the approach is different, but the objective is same. Another one is the differential evolution, which was devised by Strawn and Price. Again, you see the same thing: initialization, then mutation, then recombination selection, some variation in the operations, and then you start all over again. Then these particular algorithms are very useful in case of those problems which are non-differentiable, non-continuous. So discrete problems are quite easy to handle with this particular algorithm. So actually speaking, we have just given you some idea regarding these three algorithms: genetic algorithm, which is one of the pioneer, the first one, the first and foremost algorithm in this particular fray, and then touching upon the PSO and the DE, because this particular topic will be dealing with these quantum inspired versions of this PSO algorithm and the DE algorithm, and then applying them for automating the image clustering process. Okay, that's why we just touched upon these algorithms for better understanding. And then comes the quantum evolutionary algorithms. How to design. This is a generic procedure, not a specific one related to a particular, either a PSO or a DE or a genetic algorithm. A generic procedure may be as such like this. The difference, you just notice the difference. You first of all initialize all the parameters. That is quite evident with any optimization algorithm. And then encode the population by qubits. As I told you, because you have to encode your entire classical problem into some quantum problem. That means you have to encode the solution or the population the set of trial solutions by qubits. Qubits means you are having this complex coefficient, say alpha 1, beta 1, alpha 2, beta. This is one qubit, this is another qubit. So you prepare the chromosome as a string of qubits. Unlike in the case of a classical algorithm where you have either a real coded one or a binary coded like 0 and 1 only. But here you have these qubits which are just taking up the space in place of these bits or the real coded genetic algorithms. And then just to ensure that you are attaining, that means whether the valid qubits are there or not, whether the validity, because these are generated randomly. So to ensure that the qubits are valid or not, so you have to perform this quantum orthogonality, which ensures that alpha square plus beta square in all the cases are equal to 1. So after that, we arrive at a solution which is comprising of valid qubits. And then you come to this part is actually going to help you for the automatic part. So you see, so what was the problem? The problem was that for clustering you need to apply or need to provide some user-defined target number of classes. But in this case, what you do, you start with any, say for any value, any value n, say maybe a very high value, say 20 or 30, because we do not know what is going to be the exact number of clusters within a particular data set. So you start with a very high value, say 20 or 30. Then you assume that the number of clusters is going to be 20 or 30, although it is not going to be that, but then you start with a very high value. But not, that means you are just removing the dependency of the algorithm on providing the exact number of target classes, as in the case of the conventional clustering algorithm. So you start with, say for example, here in this case, you have this p number of clusters you start with. So this is actually not the exact target number of clusters. So any algorithm can start with a p number of clusters, not an issue. So you do not require any human intervention as such. And then what you do, so you then select randomly p number of cluster centroids, as is quite evident or very similar to any clustering algorithm. So maybe these are this one, and this one are the p number of cluster centroids which you have selected. So these are all the cluster centroids. And then again you go for a randomization process where you select some random thresholds between 0 and 1, like this threshold is phi 1, phi 2, phi 3 to phi p. So for p number of cluster centroids, you design or rather you come up with p number of random thresholds varying between 0 and 1. And then you just, because these are all random in nature, so entire process is random. So there is no point in having human intervention. So then what you do, you just select only those particular cluster centroids which are having a threshold, which have been assigned a threshold of value greater than 0.5, because this phi 1 to phi p are going to have a value between 0 and 1, random in nature. So some of the values will be greater than 0.5, some of the values will be less than 0.5. So now you just go on checking whether this particular value phi is going to be either greater than 0.5 or less than 0.5. So it may happen that some of the values are greater than 0.5 and some of the values are less than 0.5. So you discard all those or deactivate all those values, all those cluster centroids which have a threshold value, which have been assigned a random threshold value of less than 0.5, and make all others which have a threshold value greater than 0.5 active clusters. So you see, ultimately starting with a p number of clusters, which is actually a very simple number. You start with 20, 20, 30, anything you may feel like. And then you are just coming down to a very few selected number of clusters, depending on this threshold. So ultimately the algorithm, you are just enabling the algorithm to choose between the clusters and then arrive at the optimal results. So now, obviously speaking, whether you are choosing, say for example, you start with 20 number of clusters, p is equal to 20, and then end up, and after the first selection of the thresholds, you end up with 10 number of clusters which are activated and others are deactivated. So it is not that number 10 is going to be the target number of target classes, because then what you do, then you go to the next step. So this process ensures that you are ending up with only active number of clusters, some of the clusters being active and all the other clusters are deactivated, not active now. Now what you do, then you go for the entire clustering process. You use this information where you have these different randomly oriented clusters, say a subset of p, that means maybe any value between p, 0 to p, not 0 actually, 1 to p. So then what to do, then you go for the clustering process, assign the data points to the activated clusters based on some metric, either a Euclidean distance or any other distance metric. You just compute the distance and try to assign the data points to a particular cluster where the distance is small. Because objective is to have the intra-cluster similarity high and intercluster similarity high, intercluster similarity low. And now, so after this point, you have this clustering result outcome with you, the first point. So you have already assigned the data points, you have with the activated clusters, and you are ending up with some clustered outcome, maybe 10 number of clusters. And then, is that the end? No, you then go for the determining the quality of clusters, because that is the goodness of cluster you are going to evaluate using a cluster validity index. So that this process ultimately gives you some insight whether the value 10 or 10 active clusters is going to be the best possible outcome or not, or you require further refinement. If you require further refinement, obviously you have to again go for, then in the next step, you start with this 10 and then again repeat the previous process, then again repeat the previous process. Now P is equal to 10 and then arrive at say something, say P is equal to 6. And then again you repeat. So ultimately with time, you will go on reducing the number of clusters, that means merging regions together. And each time you are going to measure the cluster validity to see whether this clustering has been good or not. So now the point when you achieve that the cluster validity index is giving you insight or giving you some idea that the clustering has been very good, depending on the maximized value or the minimized value of the cluster validity index, then you stop. That means you, at that point, the number of clusters become the optimal number of clusters of that particular clustering process. So you see then what you do, and each and every time you record the index value, that is the cluster number of clusters, and number of activated clusters, and the index value, that means how many numbers are there, and then repeat until there's no change in the activated clusters. So you go on repeating the entire procedure, you go back again, and then you again just decide the thresholds randomly. So now you see that in the entire process, you do not require any human intervention as such. There is no human intervention. So the entire process becomes automated. So at the end, you end up with the automated number of clusters, the optimal number of clusters, which have been validated by the cluster validity indices and without requiring any human intervention, thus making the entire process automatic in nature. So these are very specific algorithms. We have these. I already told you that we have there are some examples of these quantum Inspired algorithms being applied to, and this is a generic algorithm which applied to PSO and D, and there are some results I'll be showing you. So you see this is a standard dataset we have used from the Berkeley image dataset, where we have used this quantum Inspired automatic clustering particles from optimization and the quantum Inspired automatic clustering differential evolution. So we've applied this quantum evolution algorithm on this PSO and D to make them quantum inspired in nature. And with these parameter specifications, we applied that on this data. Then you found, I don't know whether it is visible or not. So you see for different images, for this PSO version of quantum version of PSO, and this is the classical version of PSO. This is the classical version of D, and this is the quantum version of D. So you get that for the tools image, you get different number of clusters automatically determined by the algorithm 44464 for different runs. In this case, these are the values. In this case, for the board, for the B2 image. So each and every algorithm is giving you some outcome. Obviously, following the same procedure, with the exception that these classical algorithms are classical in nature, and these algorithms are quantum inspired in nature, resting on this quantum variation of this algorithm. So encoding the entire space into quantum domain. And then you calculate some mean and standard deviation. And finally, you see what is the outcome, because all the algorithms are equally capable of giving you the optimal number of clusters NC, like this, in different runs. So which one is better? So just for assessing the performance, we went for this Friedman test and the two-tailed t-test. So when you see from the Friedman test, you see the ranking of this QAC PSO, that is the PSO variant, or the quantum inspired variant of PSO algorithm, applied to automated clustering has been the lowest rank, which implies that QAC PSO is giving you the best performance among all the other participating algorithms. So you see now that you have been able to automate the entire process of the image clustering into, or the image clustering process into an automated clustering process without requiring any human intervention, whereby after the application of the algorithm automatically determines the number of clusters on the run. on the run, 44464 like this. So you see that is, otherwise you should not resort to this procedure. What you have to do, you have to give this value 4, 6, 5, anything you do not know to that particular algorithm under your belt, and then you run the algorithm. But that is a very critical problem in the case of real-time situations. I do not have the exact idea regarding the number of classes. So now that is all about this quantum inspired part. Now the objective, the main theme was the multi-level systems. So multi-level quantum systems are more efficient and hopefully going to be more efficient. Now whatever convention or other, whatever quantum machines, as you know, with IBM, Microsoft, Google, all these are having quantum machines. They are just outsourcing these quantum machines on the IBM, the cloud platform. Maybe D-Wave also with the annealing computers and this IBM with the IBM QSkit platform and all these things. But then all these machines are based on this qubit. That means they are actually resorting to the qubit, only the two state. That either you have a Kate 0 or Kate 1 and a combination of both. But then if you just think of something which is multi-level, higher level of quantum systems, then you go for what is referred to as a qubit. So in contradiction to a qubit, you have a qubit which maybe have as many as n number of basis states. It's Kate 0, Kate 1, Kate 2, Kate 3, in this way to Kate n number 1. So in the qubit itself, you have multiple number of solutions superposed together. Now if you go for a qubit, obviously the number of solutions which can be superposed automatically goes exponentially higher. So the efficiency automatically goes higher. So we're just touching upon how this efficiency is going to be improved. So a particular qubit can be represented like this: alpha 1 Kate 0 plus alpha 2 Kate 1 plus alpha 3 Kate 3, in this way alpha n minus 1 Kate n minus 1 for n number of states, basis states. Now, probably with the orthogonality constraint, alpha square plus alpha 2 square plus alpha 3 square is equal to 1. So now see, same thing but molded in a different way, with the exception that here you have number of states increased indefinitely. So now this is if you just recollect this representation of Kate 0 and Kate 1, it was in the case of a qubit, it was 1, 0 and 0, 1 only. But here you have n number of values like this. Kate 0 may be represented by 1, 0. In the Kate 1, it is 0, 1. Obviously, Kate 2 will be 0, 0, 1. And the Kate n minus 1 will be all zeros and the last one will be 1. So the solution space is going to increase exponentially faster. So now state of a particular ith qubit, obviously, so you have this, if you just go back, if you have this alpha 1 is actually the complex probability amplitude of this Kate 0, alpha 2 for Kate 1, alpha 3 for Kate 2 in this way. So alpha n is for Kate n minus 1. So you see the alpha n is actually going to be the deciding factor of this Kate n minus 1. Similarly for others, and then alpha 1 for 0, alpha 2 for 1, etc. Sorry. So if you think of implementing, say quantum inspired genetic algorithm, QGA, multi-level, with a multi-level quantum system, that is n-level quantum system. So what you will have to do, you have to just design that. Now in this case, obviously, you will be having the population encoded into qubits, not qubits. So in this case, however, what we have different qubits, n number of qubits are there. And each and every qubit is having n number of possible states. Alpha 1, alpha 2, alpha 3 to alpha n. So you see the amount of space for trial solutions is going to be very vast. In the previous case, there was only one single space, solution space, but now we have a maximal space of n cross n, capital N cross small n. So obviously speaking, any qubit can be represented in generic form as alpha 1, alpha 2 to alpha n. Now 2 being represented by obviously I told you, the third one will be 1 and n minus 1 will be, last one will be 1. And you can increase any n further. Now why I'm touching upon this, because these are the systems for the future. But then the existing systems, IBM, QSkit or any other platform is only dealing with qubits. There is no provision for incorporating qubit, given the advancement in technology and science at this point. So you see, if you just go for thinking or encoding a particular chromosome in a genetic algorithm using qubits, your chromosome will look like this. For example, say for n is equal to 16, you are using 16 qubits. So each and every individual part of the chromosome will be a qubit, like Q1, Q2 like this up to Q16. So now you go for initialization because every algorithm requires initialization. Now, hopefully, in this initialization, you assign the probability amplitudes of all the individual states, basis states, to be equal to 1 by root n. Because you have to ensure that the square of all, sum of the squares of all the probability amplitudes will be equal to 1. So if you go for n number of states and just go for 1 by root n whole square plus 1 by root n whole square to n terms, you will get 1. So that to ensure that the quantum orthogonality is maintained, you have to initialize the qubit in this particular form. And then now you see the interesting thing is that how the qubit is helping you to achieve the more efficiency. For example, if you just have a quantum system and you have designed a quantum chromosome n, which is guided by the precision epsilon and such area x min and x max, similar to that of encoding any chromosome for a particular problem in a genetic algorithm. You require to give the precision and require to give the minimum and maximum values. So the number of quantum system bases is given by this expression. So now if you just put n is equal to 2 over here and precision given epsilon and such area minus 1 to 1. So you see, for example, for encoding a particular chromosome n, using only qubits, that means n is equal to 2 state, you have to have at least 21 qubits for arriving at this precision. If you use n is equal to 3, that is a generic form, or rather a specific one for qubit, which is referred to as q treat for 3. You will only require 14. So you are reducing from 21 qubits to 14 q treats. And if you are using more than 3, that is, you are going for generic qubit, you require only 11 qubits. So 11 qubits are more easier to handle than 21 qubits or 14 qubits, I suppose. So that means you are gaining in terms of the space complexity, and not only space complexity, you are also reducing the time complexity. So that is why the systems are going to be more efficient if you are embarking on this multi-level quantum systems. And then, obviously speaking, that things will be different because the observation of the measurement operations and all other operations will be different in this situation because the states are different. The number of states are more than 2. So this is one typical example where you have the measurement of a qubit. How do you measure a qubit? So what actually happens is the mechanism is same, the outcome is going to be same, because in either way, either you are going to get alpha 1 square, alpha 2 square to alpha n square. And depending on whether which one of these is the largest one, you are getting that particular state attaining the outcome, or rather qualifying to be the outcome. Okay, so this is the situation in the case of observation of genes or observation of the chromosomes, so the quantum genes. And then you have the rotating gates, or the rotation operation, which are being done to manipulate the qubits so that they can be aligned to a particular state. In this case, however, not only the K0 or the K1 state, maybe a K2, K3, whatever it is. So you require this rotation gates to manipulate. And then finally, you have the disaster operation. Very interesting one, because you see, since you are using qubits, obviously you are increasing the search space, because that is why the search space is very large. And it always leads, if the search space is large and you do not explore it or exploit it efficiently, it is going to give you premature convergence, because the search space is very large. So it is high probability that you will end up with a local solution at any point of time. So it will be prematurely converging. And the probability of falling into local minima will be higher, because you have to design an efficient algorithm which will explore the entire search space, because the search space is very, very high here. So that is why an operation can be designed, which is referred to as disaster operation, which actually what it does, at any point of time, it checks whether a particular chromosome is going to be stagnant or going to just fall into a local optima. So at this point, what it does, it goes for reinitializing all the chromosomes with that particular property, which are bound to or are liable to fall into a local optima to the initial state 1,0. That is what I mean to say. You just destroy, or disaster means destroy, the configuration of the qubits at any point of time during the run of the algorithm by just judging whether the chromosomes are not fit, are not going to excel in their performance, and likely to just stick into the local optima, get stuck into the local optima. So what you do, you just pick and choose those chromosomes, and then initialize them again back to square one. That means back to the initial state, so that you can start all over again. That means because since you are just embarking on this large search space, what you can do, you can only obvious thing is that you just discard those solutions. But discarding will reduce the search space. So do not discard that. You are not discarding that. You are just reinitializing them with the initial values again to just help them to again evolve with time. And then this is one example. In the case, what you do, it actually ultimately virtually increases the population size. So you see, you first check whether the chromosome is not the best, and then you just check on the disaster condition whether it is true or false. And then what you do, you just initialize all those particular chromosomes, all those k chromosomes, from 1 to n number of chromosomes, setting their probability amplitudes to be equal to 1 by root 10, which was the initial state. This one, initial state. You just again, reinitialize the qubit again back to the previous or initial state to enable them to just compete again without discarding them altogether. So this is one typical case where you can just go for the disaster operation. And then given this disaster operation, given this rotation operation, given this observation or measurement operations, and then the encoding part, you can just redesign the quantum inspired algorithms we have already discussed into this multi-level form. Just simple, there are some simple variations. You just again initialize the parameters. Now in this case, you encode them as qubits, quite obvious. You again perform the quantum orthogonality as was done in the case of quantum, just to ensure that the qubits are valid. And then select the random number of activated clusters based on some random thresholds. Then you go for the clustering process. And then what you do, you go for measuring or the measurement, because you have to determine whether the clustering outcome is good or not by using the cluster validity indices. Now, these cluster validity indices are classical metrics. So you have to have the classical values of the outcome, clustering outcome, to determine the quality. So you go for the observation, that means the measurement of the entire system, and then you just measure the quality of the clusters using the cluster validity index. And then once you have done that, you are in a position now to see whether the clusters are good or not. Now, if it requires further refinement, you manipulate or you part up the solution by using rotation gates and quantum disaster. And then at each and every iteration, at each and every step, you record the index value and the number of activated clusters, and just repeat the entire procedure until you end up with the optimal outcome. So you see the entire thing, that means the entire process, we started all over again. We just started with the clustering process. There are its objective, its advantages, then the problem challenges associated with that, and then we just start upon the quantum computing paradigm, and then different cluster validity metrics to validate the number of clusters, or to assess the goodness of clustering algorithm, and then we finally use the algorithms and model the entire clustering problem or the clustering process as a optimization problem to optimize the number of clusters on the run. Then we just touched upon the classical algorithms, very well-known algorithms, just to have a brush up of the ideas, and then going for the quantum-inspired generic version of the algorithms, the single-level one, and then finally ending up with the multi-level quantum systems using the qubits, making the entire process automated in nature. So these are some of the references you can just go through if you feel like. And finally, I am open to any queries from you. Thank you for your patience.
Thank you, Siddhartha. We're a little bit over time, but I think why don't we just take one question that came in earlier during the presentation. And the question's from Gopal, and their question is, what are the advantages and disadvantages and disadvantages of the various clustering methods?
Thank you for your query. Because you see, I already touched upon this particular problem, because you see different clustering algorithms have been designed differently, and each and every one is focusing on a particular aspect of the entire problem. So as you have seen that we have given some examples of the TV scan, K-means, and that compute link, where you have different clustering outcomes for the different algorithms. Maybe the same data set you are using, but based on the approach, based on the distance metric they are using, based on the other factors, other parameters they are using, you are ending up with different outcomes. But all the clustering outcomes are valid, but then maybe they are not, you do not have any uniform method as such for a clustering algorithm. It depends.
Okay, great. Well, Dr. Bakatara, thank you for your presentation today. I want to thank everyone for attending today's presentation. We have just a quick programming note of our upcoming schedule. We have 2 additional webinars coming up later this month. On the 23rd, we have a webinar on job changes from our Build Your Career webinar series. And from our standards webinar series, the Data Compression Standards Committee is going to be doing a presentation on February 28th. Registration is open for all these webinars, and you'll be able to register using the link you'll receive in tomorrow's email, which, as said at the beginning of the webinar, will include the recording as well as the slides from this presentation. You can actually also register for any of our recent webinars that have happened over the last month or so. Again, I would like to thank Dr. Siddhartha Bakatara for being here today and his wonderful presentation. And again, thank you all for attending. Have a great rest of your day.
Thank you. Thank you very much, Scott. Thank you. Have a good day. Thank you.